Welcome to you all to this MOOCs online video course, Theory of Yarn Structure. We have started discussing module 8, Tensile Mechanics of Yarns. In the last 3 classes, we talked about mechanics of parallel fiber bundles, then we started discussing about stress strain relation. So, in the last class we have derived so far this relation. So, our aim is to find out a relation characterizing fiber strain and yarn strain. So, this is your fiber strain, this is your yarn strain, this is contraction ratio and beta is the angle of fiber, and we obtain this relation. Now, we will work from here. So, 1 plus tan square beta is sec square beta. We do not change the numerator. One by sec square beta is cos square beta. Show. Tan square beta into cos square beta is sin square beta. Right. Now, we expand it 1 plus 2 epsilon a plus epsilon a square cos square beta plus 1 minus 2 eta epsilon a plus eta square epsilon a square sin square beta. Then we see that cos square beta plus sin square beta plus 2 epsilon a, no, 2, yeah, 2 into epsilon a cos square beta minus eta sin square beta plus epsilon a squared cos square beta plus eta squared sin square beta. Cos square beta plus sin square beta all right. If we expand at the left hand side also, then what we obtain is square and this is equal to 1. Now, we assume that the strains are small, fiber strain as well as yarn strain all are small in magnitude. When fiber strain is small, so square of a small quantity will be further small, tends to 0. Similarly, when axial strain is small, square of a small quantity will be further small, this tends to 0. So, if we rewrite our earlier expression 1 plus 2 epsilon a cos square beta minus eta sin square beta plus squared cos square beta theta squared sin square beta. So, when this tends to 0, this tends to 0, this 1 and 1 cancel out. So, we obtain these two cancel out. So, this is approximately equal to 0, this is also 0. So, what we obtain is into sin square beta. This relation is a very important relation, because it characterizes what will be fiber strain if we apply a given amount of strain to yarn. So, fiber strain depends on yarn strain, twist angle beta and contraction ratio eta. These three quantities determine fiber strain. A long ago, in the year of 1907, a very famous scientist Gegoff reported this relation. This relation can be obtained from this expression if we obtain this equal to 0. So, this is a very special case. When there is no contraction, no radial contraction in yarn, fiber strain is equal to yarn strain into cos square of twist angle. However, this expression is a more generalized one. If we know contraction ratio, twist angle, yarn axial strain, we will be able to predict fiber strain using this relation. So, we derived a relation between fiber strain and yarn strain. Now, we would like to derive a relation between fiber stress and yarn stress. So, what is the relation between fiber stress and yarn stress? This we are going to derive now. For this derivation, we take help from this figure. What you see is an oblique fiber, if an axial force F subscript 1 is applied to this fiber, and F subscript A is the axial force to the yarn. So, F subscript 1 stands for the axial force to the fiber, whereas F subscript A represents axial force in yarn. Beta is the twist angle. The cross sectional area of the fiber is small s. As a result, the sectional area is S star. So, let us write what is what here. F1 axial force on fiber F subscript A axial force on yarn cross sectional area of fiber and is the sectional area of fiber. Right. We know that force is area. So, F1 is the force. Let us assume stress is sigma and what is the area? Small s. We assume that fiber stress strain relation is linear. So, sigma is equal to E times epsilon L, Hooke's law. Sigma is fiber stress, E Young's modulus, and epsilon L we know fiber strain. So, if we substitute this relation here, what we obtain is into S. So, axial force on fiber is equal to initial modulus of fiber, axial strain on fiber and cross sectional area of fiber. Now, we go back to this drawing again. We know the quantity of F1, we are interested to find out F subscript A, beta is the twist angle. So, F subscript A is equal to F1 times cos of beta. So, let us write that F subscript A is equal to F1 times cos of beta. F subscript A is equal to F subscript 1 times cos of beta. Okay. So, what is F subscript A? F subscript A is from here, Young's modulus, fiber strain, fiber cross section area into cos beta. Then what is the stress developed along the axial direction of yarn? What is the stress developed along the axial direction of yarn? Stress is equal to force per unit area. So, force is F subscript A. What is the area? This area is S star. So, sigma subscript A is equal to F subscript A divided by S star. stress is equal to S star. What is F subscript A? E epsilon L S cos beta divided by A star. A star we know from module 2 S by cos beta. So, A star is S by cos beta. So, sigma A becomes E epsilon L cos square beta, because you see here this S and this S cancel out. So, sigma subscript A is equal to E Young's modulus epsilon L fiber strain into cos square beta, beta is twist angle. Right. Now, we know E subscript L is equal to this form. We have derived this expression a few minutes before. If we now substitute this here, into cos square beta. So, E epsilon A cos to the power 4 minus beta. What is this expression? This expression is the axial stress of one fiber along the yarn axial direction. So, now we have to find out what is the total axial stress or total axial force developed in yarn. For that purpose, we come back to this drawing. What we see here, a cylindrical yarn, circular cross section is shown here, lot of fibers are present here. We consider an annular ring which is situated at a radius r and whose thickness is dr. So, if we find out what is the force developed force on fibers in this annular ring, then if we integrate that expression from 0 to d by 2, we will obtain the total force developed in the yarn, right. So, the total force developed in the yarn is the integration of stress into area. So, what is stress? Stress is sigma A, stress on one fiber, and so the total area available is d subscript S. D subscript S is the area of fibers available in this annular ring. If we integrate that from 0 to d by 2, we obtain the total force. So, what is ds? D subscript s stands for the elementary sectional area of fibers. Elementary substance cross section area of fibers. This we define in module 2. So, we know mu is equal to fiber area divided by yarn area. So, fiber area is equal to yarn area into mu. What is the yarn area here? 2 pi r dr into mu. So, this comes from the definition of packing density. Packing density is defined by fiber area ds divided by yarn area 2 pi r dr. So, ds becomes equal to 2 pi r dr into mu. So, now if we write this expression P sigma A ds 0 to rho by 2, then ds is equal to 2 pi r dr into mu. So, if we substitute sigma A into 2 pi r dr into mu. If we substitute sigma A here, then we will get a relatively long expression. So, P is equal to 0 to d by 2 E into epsilon A cos to the power 4 beta minus eta sin square beta cos square beta into 2 pi r dr times mu. Right. This form of integration, we see two variables, one is beta, second is r, and we know that this r and beta are related because tangent beta is equal to 2 pi r z. So, we have to either convert this beta into r or this r into beta, so that we will be able to do the integration. So, let us convert this r to beta. So, let us do that. How we do that? R. What is r? R can be written by 2 pi r z by 2 pi z. What is 2 pi r z? 2 pi r z is tangent of beta. Two pi z. In the denominator, we multiply d, capital D. Similarly, we have to do the same for the numerator. So, let us do that. D what is this pi dz? Tangent beta d. So, r becomes d tan beta by 2 beta d. Now, this d by 2 times tangent beta d is a constant, tangent beta. Right. So, dr is d by 2 tangent beta sec square beta. So, that is equal to cos square beta. Now, what is r dr? Here it is r dr, r times dr. So, d by 2 square into tan beta divided by cos square beta. So, sin beta by cos cube beta d beta. We will substitute this into this expression. So, this expression will become further long. Let us do that. So, P is equal to 0 to d by 2 into epsilon a cos to the power 4 beta to pi mu into r dr. When r is equal to 0, this will be 0, and when r is equal to d by 2, the angle will be beta d. So, the limit will change from 0 to beta d. So, what we obtain is E epsilon a 2 pi mu into d by 2 tangent beta squared integration cos to the power 4 beta into d beta. So, epsilon a 2 pi mu squared integration sin beta cos beta minus eta sin cube beta by cos beta into d beta. Right. This limit is 0 to beta d, 0 to beta d. So, we have to solve this integral. So, there are two indefinite integrals. Let us solve them. First is sin beta cos beta d beta. Let sin beta is equal to t. So, cos beta d beta is equal to dt. So, this integration will become t dt. Integration of t dt, t square by 2. What is t square? Sin square beta by 2. So, we come back and write the solution one by one. Sin square beta by 2 minus what is the next integral? Next integral is sin cube beta by cos beta into d beta. This we can write as into d beta. Let us assume cos beta is equal to u. Minus sin beta d beta is equal to du. So, 1 minus u square by u du. So, we continue integration sin cube beta by cos beta d beta minus 1 minus u square by u du. So, minus du by u plus u du minus du by u ln u plus u square by 2. What was u? U was cos beta. So, minus ln cos beta plus cos square beta by 2. So, this is the solution of this integral. We come back and we write this minus. So, minus into minus will be plus ln cos beta minus cos square beta by 2, and this will be multiplied here, this will be multiplied here. So, we will now write this. So, P equal to E epsilon A 2 pi mu d by 2 tangent beta d square sin square beta d by 2 plus ln cos beta d minus eta cos square beta d by 2. This is the first part minus second part sin square 0 by 2 eta ln cos 0 minus eta cos square 0 by 2 show what it becomes. P E epsilon A 2 pi mu d by 2 tangent beta d squared sin square beta d by 2 plus eta ln cos beta d minus eta cos square beta d minus, this is equal to 0, this is equal to 0, this is equal to half. So, 0 minus 0 plus eta by 2. What we do now, these 2 and these 2 we wish to cancel. So, E epsilon A pi mu beta d squared sin square beta d plus 2 cos beta d minus eta cos square beta d plus eta. Okay. Further, we write E epsilon A pi mu squared sin square beta d plus these 2 we will shift here because of logarithmic function eta ln cos square beta d plus eta minus eta cos square beta d. So, plus eta into 1 minus cos square beta d, that means plus eta into sin square beta d. Sin square beta d plus eta into sin square beta d. So, 1 plus eta sin square beta d, that will be the next step. So, P E epsilon A pi into mu d by 2 tangent beta d square 1 plus eta sin square beta d plus eta ln cos square beta d. This tan square beta d we will divide. So, what will become E epsilon A pi mu d square by 4 into 1 plus eta sin square beta d divided by tan square beta d cos square beta d plus eta ln So, this is the expression for axial force in yarn. Now, this quantity talks about something. What is that? Suppose we think about an untwisted fiber bundle of same count and same substance cross sectional area. Let us now think about an untwisted fiber bundle, that means parallel fiber bundle of same fineness having same substance cross sectional area. Let us now think about an untwisted parallel fiber bundle of same count is and having same substance cross sectional area. So, at same strain, what is the strain? Epsilon A. What will be the axial force? This axial force we denote by P star. P star will be equal to sigma A into substance cross sectional area. Force is equal to stress into area. What is sigma A for such parallel fiber bundle? E into epsilon A. And what is S? S is mu times pi d square by 4, since d square is equal to 40 by pi mu rho. And S is equal to T by rho, right. This we learned in module 2. So, you see this now, E epsilon A mu pi d square 4. So, this quantity is equal to the axial force of a parallel fiber bundle having same fineness and same substance cross sectional area. So, if we write now P by P star, this will be equal to 1 plus eta cos square beta d plus eta ln cos square beta d by tan square beta d. So, P by P star is equal to 1 plus eta cos square beta d plus eta ln cos square beta d by tan square beta d, same here. Now, something about this quantity P by P star. Yarn axial force divided by axial force on a parallel fiber bundle having same fineness and same substance cross sectional area like yarn. So, this quantity we denote as phi, where phi is known as coefficient of tensile force utilization. in twisted yarn. The material remains same, fiber material remains same, however, this is yarn, this is parallel fiber bundle. So, there is the influence of actually obliquity. So, this quantity characterizes structural effect in the yarn. So, coefficient of tensile force utilization in twisted yarn is equal to P by P star, which is equal to 1 plus eta cos square beta d plus eta ln cos square beta d by tan square beta d. This relation is very important because it characterizes the relation between yarn stress and fiber stress, yarn force and fiber force. Now, get off. Considered contraction ratio is equal to 0, there is no radial contraction in yarn. So, is cos square beta d. So, this is a very special case. However, this is a very generalized expression. Now, how does this expression relates to reality? What is the comparison between this expression, this theoretical result with experimental findings? Let us now learn about that. This compares theory and experiment. When eta, if we put eta is equal to 0 here, then we obtain the first curve is this curve. When eta is equal to 0.5 here, for different angles of beta d, we obtain the next curve. And this curve is something different, which is the result of another theory where crimp variability was considered. What we see is that from this region onwards, except from 0 to 10 degree twist, surface twist angle, all the experimental results are tending to fall onto the theoretical line. In this part there was little deviation was there, and that could be probably explained by some other phenomenon. It is related to crimp variability in fibers in yarn. So, in this particular part there is a very good correspondence obtained. Between theory and experimental results. Now, we would like to comment on a very well known aspect in yarn, twist tenacity relation in yarn. as it is well known that it increases and then decreases. This particular curve is the result of two influences. One influence is this, which is the result of fiber to fiber friction in yarn. The other influence we have just now learned is the effect of fiber obliquity. So, in a twist tenacity curve, this part of the curve, the reason is understood. However, fiber to fiber friction and its effect on tenacity of yarn still an unsolved problem in the theory of yarn. In future, one can attempt to solve this part of this curve theoretically. However, this part is theoretically solved. So, now we will proceed to solve numerical problems related to this module. The very first numerical problem what we would like to solve is related to fiber strain and yarn strain. The second numerical problem will be related to fiber stress and yarn stress. So, there were earlier 4 numerical problems related to Hamburger's model. So, this is the fifth problem in this module. So, how the ratio of fiber strain to yarn strain changes from center to surface of a yarn for different values of angle of twist 10 degree, 20 degree, 30 degree, 40 degree, and for different values of contraction ratio 0, 0.25, 0.5, 0.75. So, this is a problem. Now, fiber strain to yarn strain. This is your fiber strain to yarn strain. Cos square beta into sin square beta. So, we have to use this formula to solve this problem. C beta is equal to 10 degree. 20 degree, 30 degree and 40 degree. Okay. We will talk about this ratio here. It is a dimensionless ratio for different value 0, 0.25, 0.50, 0.75. Right. Now, we substitute beta 10 degree and eta 0. So, you will obtain this value 9698. Then we substitute beta 20 degree here and eta 0. So, this component is 0. So, then you will see the value 0.8830. Now, eta 0. So, this component vanishes 30 degree beta. So, beta 30 degree means 0.7500. Then (40 degree beta, eta is 0. So, this component vanishes, cos square 40 degree, what will be the value? 5868. Okay. So, when eta is equal to 0, so this component vanishes. So, this column is obtained, cos square 10 degree is this value, cos square 20 degree this value, cos square 30 degree is this value, cos square 40 degree is this value. What we see is that as the beta increases, this ratio decreases. That means, if we apply more twist because of the obliquity, this ratio is reducing. Similar manner, we will be able to solve what is this ratio when eta is equal to 0.25 for different angles of beta and for different values of contraction ratio. We will solve it in the next class. Thank you for your attention.